All right, now, why are these good ideas for good definitions? Okay, let's talk about that. Let me give you some examples now. So, suppose that you were, by the way, velocity is a vector and acceleration is a vector. So, apparently we can add velocity vectors and acceleration vectors using the math I just showed you, and in fact that is what we're going to do, and here is why it makes sense. Okay, suppose there was a ship that had a velocity in this direction, a sailing ship. Okay, let's call that VE for the engine. So the engine of the ship, the ocean liner, is moving it in that direction. Okay, on the other hand, let's say that the ship had some sails, and let's say that there was a wind blowing in this direction. So we'll call that VW for the wind vector, wind velocity. Okay, so the engine is giving a velocity, and the wind is imposing its velocity onto the ship, you could say. So then the question is, okay, so if you have the engine and the wind affecting the ship at the same time, what direction, what velocity, what total velocity is the ship going to have? Okay, now even before you took a physics class, you probably could have guessed that, well, the engine's going to push it forward and the wind is going to kind of push it to the right, so therefore it's kind of going to go forward and to the right a little bit, so it's kind of going to go diagonally. Okay, and that is correct, and with vector math you can get a precise calculation for the exact direction. So what we do is we do VE plus VW either algebraically or geometrically. So here's VE, there's VW, a copy of it, I mean. VE, VW, line them up head to tail, and so therefore the total velocity, the velocity that the ship is actually going to travel at, is right here, VE plus VW. Okay? And so acceleration will add and subtract the same way. Okay? Now, let me close with this other example. Okay? So let's do displacement. So suppose that you moved in a direction, suppose you moved with a displacement A, then you moved with a displacement B, then you moved with a displacement C, then you moved with a displacement D. Alright? And we can let's even give some names to those. Like, let's say we moved 1 mile east, 1 mile actually, no, that would be, let's do it this way. Let's do let's call this north, south, east, west. Okay, and so we're gonna make our components relative to that. So let's say A moved east, so we're going to represent 1 mile east by 1, 0, and then they went 1 mile north in the north direction. Then they went maybe 2 miles to the west, and then maybe another north. Alright, so these are all the motions. Okay, so let me draw what happened. So A, I said, was to the east, 1 mile. So there's A, there's B, there's C, and then D is just like B. So this one is A, this one is B and D, this one is C, All right. Now, if we did all of those motions one after the other, where would we end up? So, you would go. Let's see. So we could trace it out this way. We went to the right, then we went up, then we went left, then we went up again. Okay. Can you see that if you did that motion, can you see that that's the same thing as if you simply moved north 2 miles? Okay, so all of those 4 motions, 1, 1, 1, 1, it ended up that it's the same as if you moved 2 miles in one direction. Okay, now let's do a vector addition of A, B, C, and D. Okay, so then that's going to give 1 plus 0 minus 1 plus 0. And then 0 plus 1 plus 0 plus 1. That gives 0, comma 2. Okay, notice that vector addition gives us what happens in the real world with displacement. Okay, that is a powerful argument that we are defining vector addition and subtraction and scalar multiplication in the most useful way possible.